Hello, and welcome back to my series on building data structures from scratch in C. Last time we were working on the binary search tree, which I needed as the prototype for what I'm actually going to be building today, and that is a dictionary. So a dictionary is a list of items that's in not necessarily any particular order, but the way it's defined is with key value pairs. So here's an example of a dictionary. This is from Geeks for Geeks, and I'll put a link to this article in the description. And this is Python's implementation of a dictionary. And here you can see the dictionary. And the dictionary is composed of individual elements, that is these key value pairs. So here we have 1 as a key and the string geeks as the value. So this is the entry, and the collection of entries is the entire dictionary. And in Python, what we can see is that the key can be any data type and the value can be any data type. So here we have a string as the key, here we have an integer as the key, and the value is geeks in both, but here the value is an array and the key is an integer. You can use floats, you can use strings, you can use Boolean values, you can use whatever you want in a dictionary for the keys and the values. Another example of a dictionary is sort of the most famous. This is a JSON object. And a JSON object is a dictionary. See, we have roughly the same syntax, a collection of key value pairs. And the only difference really is that in JSON, keys must be strings. So when I implement my dictionary in C, I sort of have an option here. I can choose to use the Python approach that allows for any key and any value, or I can choose to follow the JSON version, which kind of restricts things a bit. And I actually want to make a specialized JSON library in the future. So I am going to go with the Python version because this is a more general dictionary, whereas this is a more specialized dictionary. So I can use any value for, or any data type for my key and any data type for my value. And that's going to necessitate that the user create their own comparison function for these. Again, I can create some generic ones that they might want to use, but if they have anything more complicated, such as if they're mixing numeric keys and string keys, they're going to need to do some work on their own. Okay, so let's get started over here. And actually, the first thing I want to do is talk about why I am using a binary search tree for a dictionary. Because a dictionary, as I said, is an unordered collection of items. There is not necessarily any particular order to them. It doesn't matter if 1 geeks is first or 2 4 is first. You could rearrange those, and the actual functionality here will be the same because you use the key to get the value. And so it doesn't matter if 2 is first in line or third in line or last in line because the key is 2 and that's what you're actually using to get the value. So why would I use a binary search tree, a structure that is ordered, to represent an unordered data type like a dictionary? And the reason is for searchability. If I use a binary search tree to store my key value pairs, and then I just use my comparison function to look at the keys of these things, it's going to be much more efficient to store these key value pairs in a binary search tree because we can make use of the log and search function binary search. So to the user, it's not necessarily going to appear like this is an ordered pair or an ordered set of key value pairs, but it will actually, in the back end, have that functionality, which allows for that efficiency. So that's the idea that I'm going for here. So let's go ahead and create our instance. So the first thing I need is a new group, and I'm going to call it dictionary. Now, I don't actually want to keep this in its own folder for a long time. It's just that I don't feel comfortable calling a dictionary a tree, and I also don't feel comfortable calling it a list. So it needs to go somewhere, and so for now it's going to go in dictionary until I make more data structures that are more closely related to the dictionary. So let's go ahead and do this. We're going to create a file, and this is going to be the basis of our binary search tree. Similar to how the node was the basis of our lists and our trees, the entry is going to be the basis of our dictionary. So we'll create an entry. And let's open the header file first, remove that, and we're just going to define a struct. We'll call it entry. And the struct is going to take two void pointers. And the reason for this is that I want them to be able to use any data type they want for the key and the value. So these need to be void pointers. We'll call this one key and a void pointer called value. And that's all this is. It's just a key and a value. And all we need is a constructor for it. So we're going to have it return an entry, and we'll call it entry constructor. And here I'm going to be using the same method of putting values into these void pointers that I did in the previous video as suggested by Tim37262, I think his name was. You can go back to that video and check his name, so you'll see what I'm doing in a moment. So we're going to pass this a void pointer to the key, and then we're going to pass it the integer size of the key. We'll also pass it a void pointer to the value, and we will also need the int size of the value. And that should be all. So let's open up this window here and our C file, and let's define our constructor. So struct entry constructor, and let's just copy and paste this next part. Okay, so what we want to do is first create an instance of an entry. So struct entry, and we'll name it entry. And at the end, we're going to return entry. And in between, we want to initialize some of those parameters. So our entry.key is going to need to be allocated on the heap since we're using these void pointers, and I want its scope to not be a problem. We'll deal with the scope ourselves. So this key is going to take malloc, which actually is going to require that I include the standard library. And so we'll use malloc, and we're going to pass it key size. And entry.value, again, we'll use malloc, and we'll pass it value size. Whoa. Okay, and then we can just use the memcopy function from the string library to actually put our values into these parameters. So let's include the string library, and we'll use memcopy. And the destination is going to be entry.key, source is going to be key, and we'll call this key size. Next, we'll do memcopy again. Destination will be entry.value, source will be value, and the size will be value size. And that's all we need for our constructor. Now I'm going to need to make a destructor for this that will actually empty it once I'm done, because remember, each of these objects, each key and value needs to separately be deallocated. So let's do that. So we'll say void entry destructor, and we'll pass it void, no, not a void, we'll call it a struct entry pointer to entry. And here we'll define it, so void the destructor, if you're wondering why I'm copying exactly the same function over here, it's because the header file is to show what it does, and the .c file is how it does it. And if someone is importing my library, they're pretty much just going to be interested in the header file. They want to see what it does. They don't really care how I do it. You're watching this video, so you care how I do it, but any given user does not necessarily care about how it does what it does. They just want to know what it does. And what we're going to do is say free, and we'll pass it entry key and free entry value, and then we will free entry. Why is that one not purple? Ah, because that's supposed to be capitalized. Let's see if that fixes it. Yep. Okay, that one's still not purple. I don't know why it's not purple. I don't really care what color it is, so it's fine. So now that we have our entry, let me actually back up a step and just say I think I forgot to put my destructor on the binary search tree. So I'm going to do that off camera separately. So that's our entry, and as you can see, it's a pretty simple object with just 2 parameters and a constructor and destructor. And so now we can create our tree, our dictionary. So dictionary, and as usual, we'll start with a header file, and we are going to just call this a struct dictionary. Make sure I spell that right. We're good. And this is going to inherit from, I keep losing my elbow off the side of this table. We're going to inherit from the binary search tree. So we want to actually include that in here. And we also want to use our entry. Okay, so our first parameter to the dictionary is going to be a reference to a binary search tree. So struct, not technically a reference, because a reference in this context usually means a pointer, and we're not using a pointer here. So just an instance of a binary search tree. And we'll call it binary search tree. And then we just need functions for inserting and removing, not removing, we need functions for inserting and searching the list. So we'll say the insert function is going to return nothing, but it's going to be a function pointer called insert. And it is going to take as its parameter everything we need to construct an entry. So we're going to pass it a void pointer to key, the size of key, void pointer to value, and the size of value. And then we'll have one for retrieving items from the dictionary. And here we have a question. So in the binary search tree, when we do the search, it is actually going to return, where is my search function? So search. It is going to return the data stored in a node object. So we're going to be putting these entries in nodes of the binary search tree. So a lot of layers here. So you have the binary, well, you have the dictionary, which contains a binary search tree, which contains nodes, which is going to contain our entries. So the data of cursor in this case is going to be an entry. And what we actually want is for it to return the value, not necessarily the entire entry. That would be superfluous. We know what the key is. We just need the value. And the value is going to be a void pointer. So we'll have a void pointer called search, and it's going to be a pointer function. And I want a little space there for simplicity, or clarity, that is. And we are going to pass it a void pointer for the key. And in both of these, we need a reference to the actual dictionary so we can access the binary search tree. So we're going to pass this struct and a pointer. Okay, that should be good to go. And what we need is a constructor for it. So this is going to return a dictionary, and we are going to call it the constructor. Now we actually need to pass this something. So the insert and search functions I'm going to define in the implementation file, the .c file. But we need a comparison function, and we need the comparison function for the binary search tree. So here we can see in the binary search trees comparison, or constructor, we have to pass it this function. And so I'm going to need to pass that from the constructor of the dictionary into the constructor of the binary search tree. And the reason for this is that I am using, or I'm allowing the user to use any type of data they want for the key. So if they're using some odd set of keys, like numbers and characters, they're going to need to tell this thing how to actually compare those. I'm not going to worry about that. I might put some in there for generic types. So if all of your keys are integers, you can use something that I write, or if they're all strings, you can use something that I write. But if you're mixing them up, you're going to need to write that yourself. And instead of calling it data1 and data2, I want to change the name to key1 and key2, just to make it clear what's going on. And we'll also want a destructor. And we'll just pass it a reference to the dictionary we want to destruct. So as usual, we will open up the windows side by side and pull up our implementation file. And what we are going to do is just define our constructor first. So this returns a dictionary. Let's just copy it. Okay, so let's first define a dictionary. And we will return the dictionary at the end. I'm not getting my autocomplete here, so let's build it. It's probably going to fail. It worked. Okay, so that's, yeah, that gave us our autocomplete. Okay, and what's the deal over here? Thank you. Good eye, Xcode. Okay, so it's going to return dictionary, and we need to initialize it in between. So we'll say dictionary dot binary search tree equals binary search tree constructor, and we're going to pass it the compare function. That way it knows what to do. And then our insert function is going to be defined here. So let's copy this and this. I'm going to put them up here as prototypes. And notice that usually, if I have a prototype in the .h file, I don't have a prototype in the .c file. So this dictionary constructor doesn't have a prototype here. But I do have prototypes for these, and that's because they are members of the struct. So these are not actually prototypes so much as they are members of the dictionary. So I need to actually keep the prototypes here, if that makes sense. So we can say dictionary dot insert equals insert, and dictionary dot search equals search. And there we go. We can simply return the dictionary and we will be good to go. So now I need to create the insert and search functions. And for this to make sense, I want to start with the insert functions, because this one kind of goes back to several of the data structures that we created in order to actually work. So in order to understand how the search function is going to work, I want to show you how the insert function works first. So let's define it down here. So void insert, and let's just copy and paste to prevent any unnecessary errors. And the first thing we want to do is create an instance of an entry. Okay, so what's going to happen here? We're going to use our dictionary, and we're going to call the binary search trees insert function. So if we go to our binary search trees insert function, here it is. So we are going to create an instance of the entry here in insert, and then we are going to tell the binary search tree to insert this using our comparison function. And this is going to put it in the tree, but it does it by putting it first in a node. So let's look at our node function. The node function is going to allocate space on the heap for a node and then call the node constructor. Our node constructor is defined over here. And I actually want to show you this one. So our node constructor is going to allocate space on the heap for the data, and then copy that data in, set the next and previous, and return the node. So interesting things are happening here. In the actual entry constructor, we allocate space on the heap for the key and the value. And then we are saying to the binary search tree, insert this object into the tree. And so it's going to allocate more space on the heap for the entry itself. That way, the one we instantiate in the constructor can go out of scope without us actually losing the entry. And then it's going to insert it into the tree by creating a node for it to go into. And it does that over here. So we are creating multiple instances of things on the heap, each one pointing to the next thing on the heap. The heap's a bit inefficient because it's sort of random where things are. In the stack, you always know that the next thing is adjacent to it. I would assume that the heap is done intelligently like that so that it's not just picking random places on the heap, but it's not quite as fast as the stack. So this is not the most efficient way you could do this. And the reason for it is because I'm making it dynamic. If I want something much faster, then I can implement a specific version of any of these items. And I'm just assuming for the general case, the loss of efficiency that I have is negligible. And in the cases where it isn't, I'll be able to recreate these so that they make use of the stack more. So that's basically what's going on. So that's why I want to start with the insert function here, is because we're kind of going way back into these objects. We're using the dictionary to create an entry, and then we're using the binary search tree to create a node, and then we are within the node, we are allocating space on the heap for the entry. It's a lot of moving parts, and that's also kind of why I like building my own libraries. If I have made every single component in this library, then I know how it works and I know what it's doing. And when I actually call something or need to make it do something, I can follow this train of logic all the way back. Whereas if you're importing some third-party library, I don't necessarily know how that's going. That being said, you can still download my library and use it. So you have been watching these videos, so you do know how it all works. So we're good to go on that front. Okay. So in our insert function, we are first going to create an entry. So struct entry equals entry constructor. And we're going to pass it key size, value size. And then we are going to use the binary search tree embedded in the dictionary to insert this into the tree. So we're going to say dictionary, this is a pointer, we use the little arrow, binary search tree dot insert, and we want to pass it, let's delete that actually so I can get the actual autocomplete there. It's going to take the, okay, we don't actually have that option, so that's unfortunate. So we're going to insert, let's just pull that up so I can actually see it. Insert takes a reference to the tree. So the address of dictionary binary search tree. It's going to take a void pointer to the data. So we'll pass it the address of entry. And it needs the size of the data. So we'll say size of entry. And that will handle all of the insertion for us. That's all that we need to do for this function. Even though this function is doing quite a lot of things, the way I've built this library makes it so that this actual insertion is really simple. It's 2 lines of code. It's multiple lines because I have a very thin window here, but 2 lines of code does all of that crazy stuff. It's really kind of cool. Okay, now let's use our search function. So we'll have this return a void pointer search, and let's just copy and paste because we can, and we're lazy. Not really, I'm not a lazy person. Okay, so our dictionary is going to handle the searching for us, but we need to be a little bit careful with how this is going to work. So our search function in the binary search tree, and let's pull up this over here. Okay, so this is going to return the data stored in the node. So we want to return not the data stored in the node, because the data stored in the node is this entry, this entire struct. And we used the key to, or we're going to use the key to find this entry. So we don't really need to to get the key again. We don't need the whole entry. We just want the value stored in it. So we're going to have to extract that separately. So we are going to say that, well, it's going to return a void pointer, yes. Okay, so void pointer result equals dictionary binary search tree dot search, and we're going to pass it a reference to the binary search tree. So the address of dictionary binary search tree, and then we're going to pass it a void pointer to the thing we want to find. So void pointer key. So the compare function that anyone defines for this needs to actually specify that we are comparing the keys, not actually the entries themselves, the key within the entry. Okay, so we actually get our result, and this is either going to return null. Did I need to? No, I don't need to specify void, and I can just put that. Okay, so this is either going to return the data within the cursor, so the entire entry, or it's going to return null. So let's do the same. So if result, so result might be null, and that will just exit. So if it has a result, then we are going to return, yes, I did mean that. We're going to return result needs to be cast as a node. So struct node. No, it doesn't actually. What does it need to be cast as? Anything? So it's going to be returning the entry as, okay, so I need to cast it as a pointer to an entry. So struct entry pointer result. And after we cast that, we actually want to get the value. Okay, so that's a bit tricky. So the search function of the binary search tree returns cursor data, and the data in this case is an entry, but it is an entry as a void pointer. So when I get my result here, it is as a void pointer. In order to access this member of the entry, I need to first cast it back into an entry, specifically a pointer to an entry. Then once I have cast result as a pointer to the entry, I can then extract the value from it. And if it doesn't have a result, we are just going to return null. So now the user can test if something is in the dictionary and they can actually get the value out of it. And it's quite simple when we have all of these layers to it. So the layers make it pretty complex, but our actual implementation of the dictionary, really simple. It's only a few lines of code, and that's kind of the benefit of object-oriented programming, is that you can sort of recycle a lot of things. And the more you get used to recycling your code, the easier it is to kind of build on top of what you already have. But I want to kind of end this with a little warning on object-oriented programming, and that is something I talked about in the previous video. It's something I try to avoid doing, and that is when you have a good idea, you don't necessarily want to apply that good idea to absolutely every circumstance. So in the case of object-oriented programming, we can look at a language like Java, where everything is an object. Literally everything is an object. Even the objects you create are objects. There is an object to represent objects. It's superfluous. It's ridiculous. And it's taking a good idea and just pushing it way too far. Object-oriented programming is great. Here's an example of where it's great. But doing something in C that has object-oriented elements is more like a tool in a toolbox than a philosophical orientation. You don't really need to have absolutely everything be an object and look at everything through the lens of objects. You can do things in different ways, and that's sort of the beauty of C. It gives you the tools of object-oriented programming without constraining you to it. So that's all for today. We have our dictionary object. Next time, I'm going to use my dictionary to actually start parsing out the header fields and body of my HTTP server. So come back and join me for that, good friends. And yeah, so if you enjoyed the video, please leave a like, subscribe to the channel, hit the bell, all the good stuff, and I will see you next time. Toodaloo.